Okay, guys and girls, welcome to Chapter 5, Unit 5 on derivatives of exponential and trig functions. These are called transcendental functions, and they're special types of functions that we'll be talking about reviewing and then talking about derivatives and some applications of these. We want to start with just a review of logarithms from the advanced functions class. I know for a variety of reasons you may have not done a lot of logarithms in advanced functions. So the first part of the unit, chapter 5, is just a short review of logarithms, and there is a worksheet um, that I've attached, and I've attached the bottom of this, and I've got some homework help and video lessons recorded for that. So the work with logarithms, we're going to talk about just a quick review, and I want you to go into Desmos and take a look and graph. Here's the lesson here. I'm going to call up in Smart Notebook here in a second, but I want you to graph. Let's start this off here. Okay, these two functions in Desmos and get them onto this little graph here, and then talk about the characteristics of it. So I'm going to let you go into Desmos and pause my video and get these two graphs going here. Okay, so in Desmos, the first function is y equals 2 to the power of x. Okay, and that's what this function looks like. Now the other function, okay, is y equals, and I need my keyboard and my functions button, and then my miscellaneous tab, and I need this function key right here, the log button. Now I need to provide the base, and it's going to be base 2, and then in my brackets I'm going to provide my variable here. And that's what this function looks like here. So there's my two functions. So I'm going to take these and transfer them to my next, just my sketch on my right here, and talk about the characteristics of it. Alright, so here we go here. So this first function, y equals 2x, I'll try my very best to graph this properly. Maybe you can change my pen tool. Okay, we'll stick with. Okay, so I've got a common point for all my exponent functions. I've got a common point here of 1, 0. So I'm going to write my characteristics of this function over here. Okay, so I've got it's always increasing. Okay, and I've got some endpoint behavior. The limit as x approaches negative infinity of my function, okay, is going to be 0 from the top. And my other endpoint behavior, the limit as x approaches positive infinity of my function, okay, is positive infinity. I've got a y-intercept, okay, where the function crosses the y-axis at 0 and 1. Okay, there's no roots. Okay, and I've also got, let's talk about the domain. Okay, so my domain is continuous over the whole entire x interval, and my range, okay, goes from 0 to infinity. Okay, my next curve, I'm going to change to red, okay, and that's the function. Okay, it's kind of a bad diagram here, but basically it's a inverse function of my original exponential function. So this was the function y equals the log function where the base is 2. Okay, so what have we got for characteristics here? This one's always decreasing. Okay, when I say always increasing and always decreasing, I'm talking about slopes of the tangent. So for the original one, the exponential function, always increasing, my slope of my tangents are always getting higher and higher and higher. And for my logarithmic function, here's my, high, the slope of this tangent would be very positive, high, and then it just keeps continuing here. So as I move from left to right, my slopes are decreasing. My endpoint behavior, I've got, the limit as x approaches 0 from the right of my function. It goes to negative infinity. And the limit, my other endpoint here, my rightmost endpoint is the limit as x approaches infinity of my function. And that's going to infinity. I've got no y-intercept. My function does not cross the y-axis. I have a root, 1 and 0, and I have a domain. My domain goes from negative infinity, and my range is restricted. So my domain, I can take negative infinity to positive infinity values. And my, but I have a further restriction here. I should have said this is my range, and my domain is just slightly different here. So it's x is greater than or equal to 0. Not greater than 0. Apologies. X is greater than 0. Or now I show you this and talk about the characteristics so we're familiar with what these functions look like. And I want to make a connection here about inverse functions. So my inverse function is the mirror image in the line y equals 4x, y equals x. So this is inverse function, and basically the idea is my exponential function is the inverse of my logarithmic function, and vice versa. Now, when we reflect, we can find inverse functions by interchanging x's and y's, or in a graph, reflecting it into the line y equals x. And I show you that and talk about that because I want to show you the characteristics. And the reason we walked you through these characteristics is look at the characteristics. If you look at the characteristics carefully, a lot of them are just the inverses of one another. So always increasing, always decreasing. My endpoint behavior connected to sort of in an inverse flavor. Look at the intercepts and the roots. The domain and the range. So those are the points I wanted to show you about these two graphs, and I also wanted to show you how to graph a logarithmic function in Desmos. So basically, logarithmic functions look like this. Basically, I've got a vertical asymptote for all logarithmic functions. They're inverse of the exponential function. If the base is less than 1, it has a tendency to go in the opposite direction. But for all logarithmic functions, when the base is greater than 1, they tend to go along the path of this red curve in function. Let's express a couple of logarithms here, and the basic idea of a logarithm is just this. So let's go with logarithmic function. How do I express this as a logarithm? So what do I do is I identify the base, and it's base 3. So I write log of base 3. Now the rest of the expression, is my answer, and it equals my power. Okay, that's always the case for logarithms. Okay, so for this one, I write log, the base is 10. Okay, my answer, I need my answer here. That 10 to the power 3 would be, okay, so I'll put my evaluated answer here, and my logarithm is equal to my power here, okay, or my exponent here. Okay, for this one, it would be, okay, I need to find my value here. I think that's 1 over 343. Okay, so as a logarithm, and I don't say these are equal, okay, so I write the log, okay, my base is 7. I can write my evaluated answer, and I say that that's equal to -3. Okay, you'll be asked to do this, and you'll be asked to go the reverse. You'll be asked to go, okay, given the logarithm, okay, so given these, can you write them as a power? And that's a pretty common question when we talk about logarithms. Okay, let's do the next one here. Okay, can I evaluate this? Okay, certainly I can. Here's the easiest way to do this. When you have a logarithm that you have to evaluate, introduce a variable, okay, and then write it as, okay, an exponent, okay, and then realize, okay, through trial and error, or through some calculations, or whatever the case may be, okay, maybe a common base technique, okay, that x equals 3 satisfies this equation. Okay, so that's a pretty common thing to do. Be aware of negative numbers, and just keep that in mind like we did in the last one. Okay, this next one I'm going to introduce, okay, a variable and write my exponential expression. Okay, and I'm going to run into a bit of a problem here. Okay, how we can find the answer to this. I don't think this is a common base. I don't think 347 can be expressed as base 4. Okay, so in the past we would do this by trial and error. That takes some time. I'm going to show you a mathematical way to do this, and it involves taking, okay, the logarithm of both sides. Okay, now if I take the logarithm of both sides, I use a rule that we're going to do in a minute here. So this becomes x log 4. Okay, that's one of my exponent logarithmic rules. That still equals the log of 347. Now I could solve for x by dividing both sides by log 4. Now I just simply go to my calculator, okay, and get, okay, an approximation. I go to my calculator and type in the log of 347, divide that by the log of 4. Okay, when there's no base, okay, in this particular question, okay, the log is written as just log of 347. It's implied that the base is 10. This was probably talked about last year in advanced functions. Okay, but when there's no log, it really is, okay, base 10. We don't have to write base 10 in here. Either way, when I get this on my calculator, okay, I just do a simple calculator step and I get 4.219. Okay, so by trial and error, that would have taken us a little bit of time, and it wouldn't have been as accurate. So that's a neat way to do this, okay, in that other form. Here are the logarithmic rules that we talked about. Here's switching it from logarithm to an exponent, and then some logarithmic rules that are going to come in handy as you do this little worksheet here coming up very soon. Okay, basically, and again, I wrote the power rules here, and notice the reverse or the inverse feel of it. Okay, if I have a product of two numbers and I take the log of it, I can break them apart by addition. Okay, and that relates to when I have an exponent. Okay, I add the exponents when I multiply my bases. Division corresponds to subtraction. Okay, the power, I can bring, that's the one I just did in the last example here. If I have the log of a number and I raise it to a power, I can bring that power down. Okay, and this equality statement here, if I have an expression where I got two different of the same base, okay, the same logarithm, and the two numbers equal each other, then we have to assume that the numbers by themselves can equal one another. Okay, we're going to finish with a very common science-based example and question here, okay, that ends this really quick and short video here. So it's a radioactive decay question. I'm given a formula for the amount that's left, and I want to find out the time that it takes to get down to 50% bacteria. So I need my initial value here, that's P at 0. Sorry, it should be A at 0. Okay. Okay, sorry, that should just be a quick, okay, A at 0. K is 180, that's my initial amount, it shows in the equation. And I want to find out what time, okay, I get when I'm down to 90 grams or 50% full. Okay, so I've just left the solution here. Okay, I'm just going to get rid of my, okay, so I plug the values back into my equation. Okay, so 90 is my new amount. I have an initial amount of 180, and I have this growth factor, this decay factor of, okay, be a growth factor if it was greater than 1. It's a decay factor when it's less than 1. Okay, so the amount, okay, is 85% for every given time. And I think in my question, my time is expressed in hours. Okay, so I do some solving for t here. So I divide both sides by 180, this line. Okay, I get down to, there's my half-life factor. Okay, because I want 50%, right? That 1/2 is 50%. Now I have to solve for, okay, an exponential equation here where I have to find the actual exponent. So next thing I'm going to do is take the log of both sides, or in this case it's the ln. Okay, we'll talk about lns in a second. This could easily be the log, okay, and that would be t times the log, might be 0.85. Log 10, okay, or in this case I've got ln. Okay, that ln is a natural logarithm. That's a special base, but either way, this process here is you just take the log of both sides, okay, and then I isolate my t, so it becomes t equals, say, the log of 1/2 over the log of 0.85, and with the calculator that just gives me, okay, my, okay, time elapsed is about 4.265 hours. So the chemical decays to 50% of its amount in approximately 4.265 hours. Okay, and that's a typical half-life question that you've done in, maybe if you've done in biology or some science, senior science classes. Okay, that's a quick review of logarithms, and you guys are going to be, okay, asked to work on a couple of these questions. Worksheet, it's attached, it's embedded in the lesson file, and go to it. Thanks, good luck.